shows the standard nth element. So that's going to get you the median. So when we're trying to figure out where to split, use nth element, and we can use the compare by structs I gave you. So that nth element, you can give it pass a parameter that says basically how to compare points. So you want to make a compare by object of the appropriate dimension and pass that. So if you have an x node, you'll want to compare by like 0. You'll pass a compare by 0 object to nth element, and it'll find the median x coordinate and partition stuff on the right sides. So that's probably the tricky part there. So I would start with the constructor. From there, the range query is pretty straightforward, and the KNN is a little bit trickier. So the range query for the bucket KNN, we kind of talked about how to do that. What about for the KNN query for the buckets? Thoughts on how to do that?
So could you just do a range query and essentially, I can't remember if you grow or shrink it.
Yeah, so if you don't have enough neighbors, you need to grow your range. So I would just use the range query in the loop for that. Yeah.
Would it work like what I did was I kept doing a loop of the range query, and if I ended up with the perfect amount of points from that, I just returned that. But if I ended up with more points than I need from that, I just ended up doing like running the distance function on the points to determine, because if I did a range query and got like 10 more points than I need, I wouldn't know which ones out of that are the ones that are like.
So I would use you can sort. I would sort the list that you have.
Yeah.
So there's the distance comparator.
Yeah.
So if you make a distance comparator, you say basically, and you pass this to sort, it will sort them by distance to the point that you put here. So if I make a distance comparator with my query point, and I pass that to sort, then it'll sort them by how far away they are from that point. So that's the useful thing there.
If you get an initial radius, is that a recommend using a static value or scaling that with like points? Or?
Yeah. So what are some reasonable kind of constraints we might have on that?
I would think it's your min-max.
Yeah, min-max. So what's kind of like the smallest unit of volume that we might look at? Yeah, so we're not actually going to find the 1 point, like even if we're searching exactly that 1 point, like what space are we actually going to be kind of looking through? So kind of the smallest like area we look at is one grid cell, one bucket, right? Because even if we, if we're right in the middle of that bucket, right, we still have to like loop through all the points on that bucket. So I would say a radius like one bucket size would be reasonable.
So the radius only goes one direction, so we find like an average of it.
So you can find the average and take half of that. I mean, you kind of doesn't really matter, but yeah, something kind of around one bucket size. So like your first search looking just in the one bucket seems reasonable to me. And it's nice if you can like just double it each time. So like something that when you double it is going to have you search more buckets. That's good. other questions?
How would you recommend structuring out on the trees as far as like functions, you know, like have a driver for your recursive?
Yeah, so I would have basically public KNN and range query functions. And then I would have private, like KNN recurse and range query recurse. And these two functions would just call these with like so these are gonna just have extra parameters basically. So like, you know, when I'm a user and I call KNN, basically all that's gonna happen is I'm gonna call the recursive function starting at the root. Right? Or maybe I'll have some, another difference. Here, this KNN is probably gonna return a vector of points, whereas this one might would take like a vector reference of points so you can add to it, like as you go. And so, but this is pretty much just a straightforward function that calls this one, and this one does all the work. I don't think you need any other helpers for this. I think for the tree ones, it's just constructor, and then the like public and recursive versions of the two queries. Other questions? All right. So today we're going to talk about another clustering technique. Yesterday we talked about k-means. How did k-means work? What was kind of the idea? So we were trying to pick like k cluster centers, and how did we pick where those went?
Use Lloyd's algorithm to.
So Lloyd's algorithm was the goal, and what was Lloyd's algorithm trying to accomplish? Like when we finally got our results, what were we hoping for?
Or I guess clusters.
So before we started, we had to pick k, so that was kind of the hard part. So once we picked k, right, how did we determine where the best places to put the cluster centers were? What were we trying to like optimize for? Yeah, so we were trying to find cluster centers so that like the distance from the points to their cluster center was as small as possible, like for overall the points. So we saw that this could work pretty well. It wasn't all that dependent on the number of points, right? So we saw an example where we had like 3 kind of blobs of different sizes, and it worked fine. It's pretty stable and fast. We saw that it didn't work so well when we had things that were like stretched out. So if we're not working with kind of circular blobs or other convex shapes, we're going to run into trouble. So if we had like things stretched out into little like ovals or ellipses, right, that didn't work so well. Or if we had concavities, right, we saw the 2 moons data set where we had 2 clusters that looked kind of like this. We saw that k-means didn't work very well here because we're just basically looking at the distance to the centers. Okay. So we're going to talk about one other kind of drawback of the k-means is that we have to know k ahead of time. We have to pick k before we can find out where the centers are. Okay. So what we're going to do here today is we're going to look at it's called hierarchical clustering. And the idea here is we are going to compute clusterings where we have k equals 1 all the way up to k equals n clusters all at the same time. And so we're going to cluster We're going to have a clustering where every single point is in its own cluster. And we're going to have a clustering where every single point is in the same cluster and everything in between. Okay. And so the way we're going to do this is with a tree structure. We are going to basically take pairs of clusters. And so you can think about it 2 ways. You can think of it as taking pairs of clusters and merging them into a single cluster. Or you can think of it kind of a top-down. We have a cluster and then we split it in half into 2 clusters. Okay. And we're just going to do this until we have a tree with all of basically each level of the tree is going to be a different k, right? So we're going to have, at the very top, we'll have 1 cluster. At the very bottom, we'll have n. And as you kind of go up the tree, you get every number of clusters in between. And we'll see there's some pretty nice advantages to this approach. Okay. So this is called hierarchical clustering. When we look at the hierarchical clustering, has a nice visualization that goes along with it, which I think when we see it, you'll recognize from, I may have seen it in, for example, like a biology class. Yeah, there's some really nice things about doing this clustering hierarchically. There's kind of 2 ways that we might construct hierarchical clustering. So let's say I have let's say I have my data set that looks like this. Okay. One way I can think about doing this is starting with the cluster that contains everything. Okay. And I'm going to draw my tree that kind of goes along with this. Okay. And then I'm going to basically split this recursively until I get to 1 particle per cluster. Okay. So I might split it like this. So I'll call this L. And this R. I can split R into its 2. This one maybe I split times. Okay. And so this is my hierarchical clustering of these 5 points. Okay. And I can kind of construct it by starting with the 1 cluster of everything and then splitting that cluster into pieces where the pieces were kind of as good of a clusters as possible. Okay. Does that kind of make sense? Okay. So this is called divisive hierarchical clustering, where I'm starting with this super cluster, and then I'm just I'm cutting pieces off as I go down this tree until eventually each node is in its own cluster. All right. So this is one way we can construct a hierarchical clustering. Okay. So this would be like a top-down approach. The other way we can attack it is by going bottom-up. So I have the same data set. Okay. I start with all of my points in their own clusters. And then I start merging. So maybe I merge these 2 clusters together. And maybe these 2. And then maybe these 3. So I get, more or less the same picture. So depending on how I choose to split and how I choose to merge, these pictures won't necessarily be the same, right? Okay, different clusters, but I can construct a clustering either way. So we're actually going to take a closer look at this approach. So this one over here, the splitting, this is called divisive. Hierarchical clustering. And here, this is called agglomerative clustering. Okay. So we're going to look at this version where we're doing merging instead of splitting. So it's just like in our political climate, really, we want to be bringing people together. Okay. So that's the general idea. Is we're going to start with each data point in its own cluster, and then we're just going to merge them until we only have one. So what's the obvious question we need to answer? I'm going to have to merge them one at a time. Yeah, the question is, which ones do I merge, right? Which ones should I merge next? Okay. So we'll start with kind of the easy case, which is when we're at the very bottom of our tree. So when every data point is in its own cluster, how do you suppose how might you choose which 2 points to merge? Yeah, I would just pick the closest, right? So seems like a reasonable choice, right? So yeah, if I just have 2 data points, I would just pick the closest. And as we've talked about a few times recently, I can decide how I measure how far apart things are. So we've kind of talked about this as the distance between points. For whatever reason, in the context of agglomerative clustering, instead of the word distance, I use the phrase similarity metric. This whole topic, the people had a problem with brevity. So this is just how you have to need some way to measure how dissimilar the 2 points are. Okay, so what is the distance between them? So we've talked about we use the Euclidean distance pretty often. So it's the Pythagorean theorem distance, square root of some xi minus yi squared. This is our familiar like tape measure distance. Another way you might measure this, depending on your data, is called the Manhattan distance. So if you had 2 points in Salt Lake City that you wanted to walk between, it's going to take you longer than this. I have to walk farther than this. How come? I can't walk in a straight line. I have to go along the grid directions on the streets, right? So that is, I just take the absolute value of the difference in each dimension. So this is going to give me a different way of measuring the distances between points. There's other stuff I can do. So I can, so the SVMs, right? We saw sort of kernel thing. So I could do like, take one of these and and stick it in an exponential, and so then things that are, once things are kind of far away, they're considered to just be, things kind of get smoothed out. Right? So I can do all sorts of crazy stuff to measure the distance between points, right? And you know, depending on my data, one of these might be more appropriate than the others. So I think for the data sets we're looking at, I think we'll probably stick to Euclidean most of the time, but you know, there are other options that that you might want to try out as well. So for 2 points, right, the distance or the, you know, I want to, if I'm merging clusters that are all a single point, right, then I just pick the two that are closest together. Go from there. What about at this level, right? Now I have clusters with multiple points in them. I need to somehow decide how close the clusters are together, right? And I'm no longer dealing with single points, right? So I somehow need to measure the distance between clusters. Any thoughts on how to do that? So average how? So I take each point in each cluster, get the different distance to the other, and take the average.
Like you want an average central location for the cluster.
Okay, so that's so those are both possible solutions. So one is I could find the centroids. And then return the distance between them. Okay, so for this example, right, the centroid might be like here and here, right? And the distance between the clusters would just be the distance between those two. So that's a reasonable thing to do. Other options we might consider? I could do randomly. So random might work. I think we'd want to be, I don't know. Yeah, I don't know how well that would work. I bet it would probably work pretty well most of the time. So you just pick 2 random points in the cluster and see how far apart they are. Yeah. I don't know if scikit does that. We'll do that for you. But yeah, adding randomness is often a good idea. We could pick particular points in the clusters. So instead of picking randomly which 2 points we're comparing, how could we like pick which ones are special? The closest, right? So one thing I do is the distance between clusters is the distance between the closest points. Okay, so that's one opportunity, one possibility. What's kind of the inverse of this, or the counterpart to that? Pick the farthest. Okay. So instead of looking at the smallest distance between the clusters, I look at the largest. I could also get all the distances between all the pairs of points and then take the average. Okay. All right. And the last one we'll talk about is a little bit weird, but this one basically, we pick the one where if we merged these, the distance from particles to centroids will be smallest after the merge. Does that make sense? So we look at all the possible merges, and then we pick the one that would be best in terms of reducing the particle to cluster distance. So this isn't exactly measuring distance. This is like measuring the minimum distance between any pairs of clusters. We pick the one that gives us the lowest cost after merge. All right. So, like in this case, if we pick to merge these two clusters, right? Then afterward, like the distance from the points to the centroids is going to be pretty small. Whereas if we've chosen to merge these two clusters, it would be pretty big. Right? So we'd want to pick these two. Okay. All right. So this measuring the distance between two clusters, or choosing which two clusters to merge. These are all kind of reasonable options. Okay? And so as data scientists, we need to choose between these for a data set. The term for this, again, overly verbose, is called the linkage criteria. How we choose how to link the clusters. And all of these ones are popular choices with names. So this would be called the centroid linkage. The closest points, this is called the minimum or the complete linkage. We could do the average linkage. If we look at the maximum, we call that, oh, sorry. Oops. So the minimum is actually called, sorry, the single, and the maximum would be the complete. So yeah, the minimum linkage, like we're kind of looking at a single pair of points, whereas the maximum we're kind of looking like the farthest extent of the clusters. And this last one here, where we look at which ones would be the best, would give us like the best clustering after a merge. This is called the Ward linkage. I assumed it's named after the person that came up with this method. All right. So this is the linkage criteria, right? When we do hierarchical agglomerative clustering, where we're merging, we have to decide, okay, how do we pick the two clusters that we should merge next? And they're all kind of based on some way of measuring the distance between two clusters. All of these ones that kind of deal with actual distances are nice and convenient for the single point in the cluster case, right? We're at the very bottom of our tree because all of these are basically the distance between the 2 points, right? Whether we choose the centroids, which will be at those points, or the minimum or maximum distance, which will be the distance between those 2 points, or the average, it will be the distance between those 2 points. So those are kind of convenient from that perspective. Where here we have to consider kind of all of the ways we might link them together and pick which one's best. Right. So that's the general idea of this bottom-up hierarchical clustering, right? We just start with every particle in its own cluster, and then we just pick the best pair of clusters to merge, and we just do that over and over again until we have a single cluster at the end. Any questions about that general idea?
So how do I go through, go down until there is only one cluster left?
We don't always know when a good stopping point would be, right? So we just go all the way. We don't have to use, we're not going to use that single cluster for anything probably, but it's like a good place to stop.
Okay, so afterwards we might just go along the trees to see which one gives the best.
Yeah, so we'll, yeah, that's the next thing we're going to talk about is, okay, I've done this hierarchical clustering, how would I use it? So, the way that we can make sense of our hierarchical clustering is through the basically pictures of these graphs, which are called dendrograms. So they're tree graphs, I guess, tree pictures. Or finger pictures, whatever. So this is an example of a dendrogram, okay? And all it is it's just a drawing of the tree. Okay? The horizontal axis is totally arbitrary, so the points are ordered here just so that we don't cross lines very often. Okay? So the fact that this point is opposite from this point does not mean anything. Okay, the horizontal position is just chosen for aesthetics. Okay, the horizontal position of the points does not mean anything. Okay, so that's very important. Okay. The vertical position is very important. Okay. The vertical position tells you basically the point to cluster distance for the points in that cluster. Okay, so it's like the cost of the cluster. So, if my cluster was formed very low, what does that mean about the points in the cluster? So if the height measures kind of the distance to the cluster center, if my cluster is low, what does that tell me? The points are close together, right? So this is going to be like a tight cluster. If my cluster is very high, what does that tell me? The points are far apart, so probably this probably doesn't really make a lot of sense as a cluster. So this gives me a great way to pick something like K, because I basically just start at the top and I just kind of slide my line down until I get to a point where where my clusters are all kind of reasonably close together, or sorry, reasonably low cost, right? And then I could use those K clusters. And so as I slide down, I'm basically adding one cluster each time I cross one of these horizontal lines. Okay? And I kind of just stop when I'm happy with the clusters that I have. So this is how I would go about, sort of how I would use this hierarchical clustering. One way would just be to use it as a way of getting K clusters and having kind of a good way of choosing what that K should be. So, right, so from here to here, right, that's a big jump in like similarity, right? So this is probably too few clusters and this is an improvement, right? Going down from here to here, it's less of a significant jump. So I could, it might make sense to stay here with 2 clusters, or I could come down here with 3 clusters, and it kind of depends on the application. Yep.
When you have like a huge tree, how do you decide you're at a good stopping point?
So usually for the big trees, the bottom is going to be like super crowded, and once you get towards the top, right, there's only a few like kind of branches left at the top. So you could go down pretty far if you wanted a bunch of clusters. But if you're expecting a small number, like it really doesn't matter how crazy stuff is down here. Up at the top, it's going to be like pretty calm and not that many branches. Okay. So the dendrogram, the height tells us basically how similar the two clusters that were merged are. Okay. So if they're high, they're not that similar. If they're low, they're very similar. Right? The horizontal placement is arbitrary, so basically ignore it. Okay. And then we can kind of think about sliding something down. So when we get down to, clusters that are similar enough, then we can kind of use that to pick our K. People have probably seen a picture that looks like this before in science classes. Probably wasn't a binary tree like this, but does it look similar to anything you've seen before? Like what?
The phylogenetic tree.
Yeah, it looks like the phylogenetic tree, kingdom, phylum, class, order thing. Right. So we have this hierarchical clustering of life, right? So again, we have this nested bunches of clusters, and we understand the relationships between all of our data through basically a clustering technique. So you could imagine trying to create a tree like that by coming up with some similarity, dissimilarity metric, some distance metric based on something in DNA. Right? So you have some sort of genetic way of measuring distances, and if you ran agglomerative clustering on that, you might come up with something that looks very similar to the tree of life in your biology textbook. Right. So any questions on this sort of general idea? Right. So where we don't know the number of clusters ahead of time, so we just try all of the numbers of clusters, and then we can kind of look after the fact and see. First, we see these hierarchical relationships, which can be useful in their own right, and also we can pick sort of a good K based on what we learned from this. All right, cool. So let's take a look at some code. Get our first look at a data set we'll become very familiar with over the next few weeks. And we'll compare some different, we'll compare k-means and hierarchical clustering. All right, cool. Yeah, don't tell anybody I did that. All right, so here we have an example of a hierarchical clustering in a dendrogram. So yeah, as you can see, like the bottom here gets kind of crazy, but if you look at the top, right, we have 2 clusters, then 3, then 4, 5, 6. So looking at it from top down, as long as we don't go too far down the tree, it's not that difficult to interpret. So the various linkages that we talked about. So we could look at the maximum distance between any points, look at the minimum distance between any pair of points, the average, so look at all the distances and take the average, the centroid distance, or the ward. So here we're looking at the total inner cluster distance, so that's what we were measuring with k-means. We just pick we merge the pair that reduces that by the most. So, so we'll look at the blob data set again. So just 3 kind of blobs. And we're going to use a agglomerative clustering on it. So here we'll use the average linkage. The affinity is another, like a third name for the distance. So here we're just using the Euclidean distance between the individual points. And then, so here we're saying for our clustering model, we'll pick 3 clusters, right? So we're fitting the whole hierarchical tree, and then we're basically sliding down until we're going to split that twice, so we get 3 clusters out. And as you can see, we get basically the same clusters we would get with k-means. If we look at the dendrogram of this, this is what it looks like. So as you can see, so very dissimilar, right? And so below here, all these are really close together, right? So it looks like cutting off here is the right number of clusters for us for this particular example. And again, these 2 points are close together horizontally. They could correspond to, so one of them corresponds to a green point, and one of them corresponds to either a blue or a red point. Right? They are not close together. Right? So the green point, all of these ones on this left are green points. None of them are close to to any of the other points. So horizontal ordering is just to make sure that we don't cross the lines. So we'll take a look at the 2 moons. So we saw with the k-means that this is kind of a hard data set to do clustering on because it's concave, right? We have these weird shapes. And so just looking at distance doesn't, it's hard for us to separate the two clusters. And by default, so we're using the complete distance, or the complete linkage, so we're looking at the farthest pair of points when we want to merge clusters, and just Euclidean distance. And so by default, right, the agglomerative clustering doesn't work that well either. So for some reason, we're merging clusters in this region with these, and so we're not getting very good clustering here. A cool thing about the agglomerative clustering is we can add constraints. So we can say, we can limit which clusters get merged by adding some constraints. Right? So what we're going to do here is we're going to say, this connectivity thing here, we're going to, for each point, we're going to find its k nearest neighbors. Okay. So we're going to find the 10 closest points for each point. Okay. And then we're going to add that as a constraint when we do clustering and say basically you can't merge clusters that don't have like neighbors that are shared. Okay. So for all these red points here, right, their neighbors are going to be here. None of the points in this shape are going to have neighbors that are across, right? So we're going to prevent merging clusters that are from the 2 different regions. Right? And so if we do this, we can actually, our clustering can actually split these 2 things apart because we've added some constraints. So we've added rules, extra rules about which clusters can be merged as we're building up this tree. So we can handle some concave shapes with the collaborative clustering.
But would that be supervised learning since we know when to merge, when should not merge?
Is sort of. So here, like, we're not really, we just said, you know, don't merge things if, like, it's further than 10, you know, if they don't have any neighbors in common. So it's not quite, we're not quite giving it a label, right? This is still kind of an unsupervised thing, right? We're just saying, hey, like, if there's no neighbors in common, then don't merge them. So it's still not really a super, like, we don't have a right answer here, really. So I would say this is still pretty unsupervised. So let's take a look at the iris data set. So, here we'll use the ward linkage and 3 clusters, because again, we know there's 3 types of iris that we care about. And again, we split out the greens pretty nicely. The reds and the blues are mixed in a little bit. And since we know we have ground truth labels, we can look at the homogeneity and completeness to see if we did a good job. And we got 76% accuracy, so I think this is like slightly higher than we got with k-means, but pretty close. So if we just look at basically a bunch of different possibilities, so we can look at the different linkages. So if we use ward, average, complete, if we look at the, if we use Euclidean distance or Manhattan distance, so this is like Pythagorean theorem or the absolute value way of measuring distance, versus just k-means with 3. We can compare all these various models and see how they do. So they range in accuracy a little bit. So k-means is worse than everything except for this complete linkage one. So complete linkage in this case is the worst. So measuring clusters by the farthest point, I guess, is not a good idea for this data set. Everything else looks to be pretty close to equal good, but the winner was the average linkage. So for this particular data set, that seems to be the best choice. Another way we can measure distance is through the correlation, which is one of the descriptive statistics we talked about. A way of thinking about this is it's instead of comparing the distance between things, you can sort of think about it as comparing like the angle between things, whether they're kind of pointed in the same direction. So that might make sense for some data sets. So yeah, just another option in our tool belt. All right, and then the last example we'll look at is through this great data set called the MNIST. And what this is it's handwritten digits. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And they are like scaled and normalized to be 8 pixels by 8 pixels. And they're all nicely labeled for us. So really, probably this is more of a classification data set, but we can use it for clustering because we know there should be 10 clusters, there should be a 0 cluster, a 1 cluster, and so on. Yeah, we'll look at this data set a bunch of times because it's just a great data set. So the post office, I believe, was one of the first organizations that really used like machine learning kind of classifiers, and it was for basically reading zip codes on handwritten mail. Long history of this. So We have 10 classes, 180 examples in each class. They're all 8 by 8 pixels. And so I guess the integer is probably from 0 to 255 for each pixel, the brightness. These, they're really low resolution. So I feel like doing classification as a human would be pretty hard with this. It's kind of remarkable how well we can do with the clustering or classification algorithms. So these are just some examples of the input. So these are built into scikit-learn, so we can just say load digits to get them all. And they have the data is the 8 by 8 image for the pixel or for the digit, and then the target is the number it's supposed to represent. So we'll just draw a few of them. So we're using the IM show to draw the pictures, and so we have about 1,800 samples, and these are some of the digits. So some I think are kind of easy to pick out, some are really hard. So this is the data set we're working with, and we'll see it a bunch. Okay. So first thing, maybe we'll just throw down some k-means, right? We're going to try it 10 times, right? So the number of initializations, which means we're just going to we're going to restart it and rerun it 10 times and see which one's the best, right? Because the final cluster locations are kind of sensitive to where we start. And we'll just start, we know we have 10 clusters because for this data set we know something ahead of time. And then we'll just look at the homogeneity score, which tells us basically how many of the, which percentage, tells us the percentage of points in each cluster that are the same class. And so if we do this, we get about 60%, which is pretty good, right? So guessing, we would expect to be about 10%. So we're doing a lot better than guessing. And I mean, what is this one supposed to be? I guess that's a 2. Like, some of these are pretty hard to figure out. Hey, what is this one supposed to be? Any thoughts? 6? So we think this is a 9 or a 4? And this, what about this one? 3. I don't know, right? So like, some of these seem like impossible to classify correctly, so who knows? And we hit 60% with k-means. Cool. So we'll do the same thing with the agglomerative clustering. So if we'll use the Ward linkage and just Euclidean distance, and if we do this, way higher, 75%. So what we're doing here is, we're kind of starting with the digits that are similar, and then we're just merging together groups that are kind of similar until we get to 10 groups. And for this particular data set, that seems to be a much better approach. So I guess this lets us get clusters that are not necessarily convex, right? Because we can merge clusters, and we could get clusters that would be impossible if we just put down the centers and said go to the closest point. So we have a little bit more freedom with the agglomerative clustering. So we'll just take a look at a few different approaches we might do. So the k-means that we used, I think we just started with random positions. So maybe if we have better initial positions, by using k-means ++ to put down the original 10 points, maybe that'll be better. I think this is exactly what we did before. For the agglomerative, we could use the ward with Euclidean, which I think is what we did. We could also try the average with the Manhattan. And looks like the hierarchical with the ward was pretty good. Maybe let's try a couple of other agglomerative approaches. So maybe let's try the ward with Manhattan. And maybe maybe try a complete. And maybe a minimum. Oh, well, we're not going to do that one. Like, so the minimum Euclidean is really bad. Wow. Wow, those are incredibly bad. Huh. That's a bit surprising to me. It looks like the hierarchical ward seems to be by far the best. So, yeah, it looks like there's a pretty big impact on how we measure distances and how we choose to merge for this particular data set. Yeah. So any other questions about hierarchical clustering? So the key, I'd say the key things are kind of understanding how we build them up, the different choices we have in terms of how we pick which clusters to merge, and then understanding how to read a dendrogram. Kind of the key pieces. All right, cool. I guess we'll end a little bit early and have some work time on the project. Hopefully nobody's disappointed about that. So we'll work on that for the rest of class, and hopefully I can answer your questions. Yeah.